So, dear friends, welcome to this new lecture number 8, where we are going to discuss the degrees of freedom, generalized coordinate and configuration space. Okay, so let us start with degrees of freedom. You know it from elementary classes that degrees of freedom is nothing but the independent coordinate. Okay, independent coordinates that is required to specify the position and configuration of a dynamical system. Okay, so independent coordinates which is required to specify the position and configuration of a dynamical system. So the question is how you can calculate the degrees of freedom. Okay, very simple. Degrees of freedom is denoted by n. In some book it is taken as small f, but here I am going to take small f as the reaction forces. Okay, so I will not consider small f as degrees of freedom. I will consider n as the degrees of freedom. Okay, is it clear? So n is the degrees of freedom, and you can calculate degrees of freedom by n is equal to 3n minus k. Okay, this is the formula for degrees of freedom. What do you mean by k? K is nothing but the constraint equation, and you know constraint equation very well in holonomic and non-holonomic. Okay, most of the cases we are going to deal with holonomic constraint. In that particular case, what was the constraint equation? The constraint equation was f of r1 vector, r2 vector, rn vector is equal to 0, and this is nothing but function of position vector. If time part is taken, it is reonomous holonomic constraint. Okay, so n is equal to 3n minus k, where k is nothing but constraint equation. This is known as constraint equation. Okay, why it is called equation? Because it having equal to sign. Okay, it is having LHS, it is having RHS, and it is obeying the equality policy. Okay, equality principle, and non-holonomic obeys inequality principle. Okay, so n is equal to 3n minus k. Okay, now the question is why 3n? Why not 6n? Why not 10n? Okay, why it is 3n? So let us understand this by taking a very simple and familiar example. You all know this. Whenever I take a Cartesian coordinate system and if I place a single particle, then how much coordinate is required to specify the position of this particle? You know the position. How you can find the position? Position is nothing but the location. That means you have to choose a origin, and from origin you have to see from x how much distance it has covered, from origin how much distance it has covered in y, and from origin how much distance it has covered in z. Okay, so you can find the number of coordinate is x, y, z. That means total coordinate is 3. If I take a system which is having n number of particles, then how much coordinate it requires for a single particle? For a single particle, the number of coordinate is 3. For n number of particles, the number of coordinate will be 3 into n. Are you getting my point? If there is a single particle, then the number of coordinates that is required to specify its position is 3. If you are taking n number of particles, then the number of coordinate which is required to specify the position is 3n. Okay, that means if you take 2 particles, the number of coordinate is 6. Like this you can get the result. Okay, so this is nothing but 3n. So you know why it is coming 3n. So you can calculate n by simply finding 3n and by subtracting k, where k is nothing but constraint equation. This is degrees of freedom. Next thing that we are going to discuss is configuration space. What do you mean by configuration space? Is nothing but the set of the position vectors of all the particles which is involved in the system. For example, if I am drawing a set like this is a r1 vector function of t, r2 vector function of t, and this is rn vector function of t. What is this set? This set is known as configuration space. Okay, this includes the position vector of the first particle, position vector of the second particle, position vector of the nth particle, where n is nothing but the total particle. You don't know what is n. Here n may be 5000. We are having 5000 particles, and you take the position vector of the individual particles and you give a set, you give the collection, and that particular collection is known as configuration space. So you have to understand this. This is known as configuration space. Okay, next question is, can we find generalized coordinate from these degrees of freedom? Answer is yes, definitely you can find it, the generalized coordinate from these degrees of freedom. So let us find the generalized coordinate from these degrees of freedom. So how we can find this? Let us see with an example. Degrees of freedom, how you will represent the degrees, how you will represent the generalized coordinate. The generalized coordinate is represented by q1, q2 up to qn. Okay, note it here, small n, not capital N. So this small n is nothing but degrees of freedom. Degrees of freedom. Okay, are you getting my point? Degrees of freedom. Okay, so here the small n is nothing but the degrees of freedom, and you know how to calculate the degrees of freedom. Once you know the value of degrees of freedom, you can find the value of generalized coordinate. Okay, and you can see here n is independent of the constraint equation because you are eliminating k constraint equation. That means it is independent. So generalized coordinate is independent of constraint equation. That is very much important. Okay, so you can analyze it very well, that n is what? 3n minus k. What you are doing? You are eliminating, you are getting rid of the k constant equation. That means what? Generalized coordinate. How you can draw generalized coordinate? You can draw generalized coordinate by finding the degrees of freedom, q1, q2 up to qn, where n is the degree of freedom. Okay, so here the generalized coordinate, okay, generalized coordinate is independent of the constraint equation because generalized coordinate is extracted from the degrees of freedom, and degrees of freedom are independent of the constraint equation. That's why the generalized coordinate are independent of the constraint equation. Okay, another question is, can we get a proper transformation equation where we can relate the position vector with the generalized coordinate? Answer is yes, we can do this. If I am having a position vector, suppose I am having r alpha, so I can transfer this to the in the form of generalized coordinate. So let us understand how we can do this. Okay, how we can do this? Okay, very simple. Okay, 1 minute, r alpha. Okay, 1 minute. Another thing that I forgot to tell you, that is this set r1 vector t, r2 vector t and rn vector t will satisfy constraint equation. Okay, you have to understand this. It will satisfy the constraint equation. So what is the constraint equation? In most of the cases, the constraint equation is holonomic. You have to get it. Okay, if time is there, it is rheonomous holonomic. Okay, in most of the situation you will get holonomic constraint equation. So it will satisfy constraint equation. So how we can write this? This is f of r1 vector t, r2 vector t. Okay, similarly here it is capital N. Okay, I have made it wrong, but you should not make it wrong. Okay, this is capital N, number of particles. So here you can write rn vector t, which is equal to how much? 0. That means this set having the position vector of all the individual particles up to a nth particle, it will satisfy the constraint equation, and constraint equation is nothing but the holonomic constraint equation, because if you deal with non-holonomic case, you require very advanced mathematics. So in this particular course we are going to deal only with the holonomic situation. Okay, so it will satisfy the constant equation, means holonomic, so which is equal to 0, and it is containing time, so you can say it as a rheonomous holonomic. Okay, if it is not having time, it is known as scleronomous holonomic. Okay, so this is configuration space. Now what we are going to discuss, the transformation equation. Okay, what are the transformation equation? That is how to get generalized coordinate, from the position vector. Okay, So if it is R of alpha, what is R of alpha? Alpha-th particle, alpha-th particle, not alpha particle. Okay, if you consider alpha particle, it will be a different case. You are considering inside the nucleus alpha, beta, gamma. Okay, we are not doing this. Alpha-th particle, that may be 1, that may be 2, that may be 3, anything. Okay, that may be n also. Alpha-th particle, and the position vector is alpha or subscript alpha is equal to R of alpha q1 q2 up to q small n. Okay, so this is the transformation equation where you can relate the position vector with the generalized coordinate. Okay, are you getting my point? And if you involve time, so it is t. Okay, so this is the position vector of first particle. For first particle it is 1, second particle it is 2, third particle it is 3. You know it very well. Okay, so here what we are going to do, we are going to find the generalized coordinate. How you can find the generalized coordinate? By simply calculating the degrees of freedom. How you can calculate the degrees of freedom? By this formula, 3n minus k. What is this k? K is nothing but the constant equation. What is constant equation? Constant equation is nothing but the holonomic constant equation, that is function of position vector is equal to 0, and this position vector, this r vector will satisfy the holonomic constant equation. That's why I am writing as function of position vector r1 vector, r2 vector up to rn vector is equal to 0. So it is satisfying the constant equation. Okay, if it is satisfying the constant equation, what is happening? You know the troubles in constant equation. Okay, you know the trouble that in constant part, what is the trouble? Coordinates are no longer independent. That means the position vectors are no longer independent. While the generalized coordinate does not satisfy the constant equation because you are eliminating k. Okay, so it is not satisfying the constant equation. That means it is independent. Generalized coordinate is independent as n is independent, small n. Okay, but this is not independent. Okay, dear students, you have to remember this. R is not independent because it is satisfying the constant equation. Okay, if it is satisfying the constant equation, you know the troubles that is the major issue. Okay, if we have the constraint, what are the major issue? If it is satisfying the constant equation, if it is satisfying, position vector will satisfy the constant equation, and I am having this. Okay, if it is satisfying the constant equation, that means the position vector are no longer independent. Okay, so it is position vector are no longer independent. Are you getting my point? Okay, independent, but it is not satisfying the constant equation, so it is independent. Okay, independent. So it is independent, but it is no longer independent. Okay, position vector are no longer independent because it is satisfying the constant equation. If it is satisfying the constant equation, what are the major issue? If we have constant, coordinates are no longer independent. For example, x square plus y square is equal to 5 square. So the moment you take the value of x, y is fixed. The moment you take the value of y, x is fixed. That means the coordinates are no longer independent. You have two set of value. One is 3 4, one is 4 3. That is fixed. You cannot take any arbitrary value. They are no longer independent because they are satisfying the constraint equation. Okay, so if it is satisfying the constraint equation, basically holonomic, okay, these coordinates, these position vectors, okay, are no longer independent. Okay, so you cannot consider position vector as independent, and we will deal this in Lagrangian formalism. And this q means generalized coordinate, which you have got from the degrees of freedom. They are independent. Thank you. So next lecture will be on the allowed configuration and the virtual displacement and D'Alembert's principle. Okay, thank you.